Okay, good evening, everyone. I'm Bhalchandra Joshi from National Center for Radio Astrophysics, Pune. And I'm going to talk today about discovery of gravitational wave, but at a frequency range very different from where the gravitational wave have been discovered. And I'll sort of explain how these gravitational waves would be discovered using a celestial detector, astronomical sources, which are excellent clocks. And so that's the main theme of this particular talk. I'm sort of delivering this talk on behalf of the Indian Pulsar Timing Array Consortium in PTA, which is a consortium of about 27 astrophysicists, postdocs, and graduate and undergraduate students. So let's begin. Okay, so what is pulsar timing array? Pulsar timing array is an experiment to discover gravitational waves. Okay, that's the broad summary of my talk. But the difference between the gravitational waves which the pulsar timing array is sensitive to and what the LIGO is sensitive to is that they are in a different part of the spectrum. In fact, they are in the other end of the spectrum than those discovered by LIGO. And that end of spectrum is ultra low frequency gravitational waves, which is of the order of nanohertz or microhertz. So the question then occurs, why look into this part of the spectrum, or why do we want to discover gravitational waves in this part of the spectrum? So to sort of illustrate or explain that clearly, let's go to the other messenger, the most popular messenger in astronomy, which has been around for several centuries, the electromagnetic messenger. And that electromagnetic messenger also has a spectrum. And this slide shows the spectrum varies from few tens or hundreds of meter wavelength to almost the nuclear dimensions, from radio waveband to X-rays, gamma rays, and very, very high energy gamma rays. And you could, in principle, observe the universe or the objects in the universe at any of these wavelengths. And it is in the electromagnetic messenger that the versatility and the complementarity of observations at different part of the spectrum sort of has come about as something which is very beneficial and useful for astronomy and astrophysics. And the reason for that complementarity is that the different wavelengths, they provide different pictures of our universe. The optical waveband, which has been there ever since the Galileo's discovery about 400 years back, mostly traces the thermal radiation. And for several years, it provided us knowledge about the stars, their temperatures, their radii, the distance these stars are. And by using these measurements, astronomers and astrophysicists were able to sort of come to a conclusion about what is the physics of these stars, what is the equation of state of these stars, how the energy is generated and transported from the center of the star to the outer part of the star, what is the kind of masses of these stars and what is their dynamics. But that was not really the full picture of our universe. So when in 1930s, almost 100 years back, the radio waves were discovered to come from the center of our galaxy, a completely new window opened, which provided a very, very complementary picture of the universe. And this radio window was more sensitive to non-thermal radiation, radiation which is not black body radiation, but arises because of other radiation mechanisms, and sort of gave us a magnetic picture of the universe, because much of this radiation involved magnetic fields. It involved gas flows and so on and so forth. And also the thermal radiation which we observed in this waveband came from the relic radiation of the universe, the hot Big Bang, the cosmic microwave background radiation and so on. And it opened a completely new window to physics at extreme for the evolution of the universe and to understand what are supermassive black holes, which came in the form of quasars and so on. Much more recently, about 30 to 40 years back, the high energy window of the electromagnetic spectrum got opened. And now we have X-ray and gamma ray observatories out there in space doing these observations, which give us a completely different picture of some of the most violent and energetic phenomena in the universe. So the point which I'm trying to make here is that looking at the same object or the same universe at different wavelengths provides a very complementary picture and gives you a much better and a wholer understanding of the physics which we are studying and the astrophysics which we are studying. And the same is true for gravitational waves. Just to illustrate my this sort of a discussion with an example, I'll sort of quote the discovery of the quasar. The first quasar which was discovered from a survey carried out by Cambridge using a radio telescope at about 100 megahertz. And they compiled a catalog of radio sources. And the 273rd source of the catalog, known as the third Cambridge catalog, 3C273, turned out to be something which had very enigmatic stars apparently associated with it. Okay. So the source was a radio source, but later on it was found that there are stars nearby. And although they look like normal stars, as the picture on the left shows, they are from very high redshifts. In fact, the redshifts are so large that they are very much at the edge of the universe. And this radio source was a powerful radio source. So the moment you place this radio source at the edge of the universe, it becomes a super powerful radio source, and the energetics of that source would have been fantastic. And a lot of work was done to get the optical star, the radio star, the so-called radio star associated with this radio source. And Sir Martin Schmidt was one of the persons who actually worked quite hard to get the two locations there together. And eventually the optical star and the radio source were sort of co-located. And that's how the first quasar was discovered. Okay. So this is just one way of sort of illustrating how there is complementarity between different wavelengths. Another good example is this galaxy called Centaurus A. And what you see here on this plot is a composite image made out of X-ray observations, optical observations, and radio observations. It hosts a very massive black hole, about 55 billion solar mass, and these black holes will be important for the later part of the talk. And you can see the complementarity between the different wavelengths very clearly in this picture, where the optical picture tells us about dust lanes in the galaxy. The radio picture tells us about relativistic particles moving in jets, and the X-ray picture shows you the picture near the supermassive black hole, which is there. So to understand this object clearly, you need observations from multiple wavelengths or multiple frequencies. And the same thing is true about gravitational waves. So the point which I was trying to make is that what is true for the electromagnetic messenger is equally true for the gravitational wave messenger, which is a very new window to the universe, which has opened only 3 to 4 years back. And the difference in different frequencies would be in terms of different sources, different astrophysics, and different physics. Okay? So the sources which you observe with LIGO are stellar mass black hole binaries, neutron star binaries, whereas the sources which you will observe with pulsar timing arrays are supermassive black hole binaries. The astrophysics which one would probe as a function of the different frequency band detectors would be different. And the physics which you would test would also be different in different frequency ranges. And sometimes you may find synergy between the LIGO observations versus the space-based interferometer LISA versus PTA and so on. So it's important to cover the entire gravitational wave spectrum. And we are going to look at the lower end of this particular spectrum, which is sort of shown here in this particular plot. The x-axis is frequency in hertz. And as you can see, the ground-based interferometers are of the order of few tens of hertz, whereas the pulsar timing array, which I'm going to talk about today, is essentially at 10 to the power minus 7 to 10 to the power minus 10 hertz. So microhertz and nanohertz. And the main source for that would be supermassive black hole binaries and their mergers. So what are the sources of gravitational waves? In general, for producing gravitational wave, you need a system with changing quadrupole moment. And the most natural choice for such kind of a source, for a continuous persistent source, would be a binary system with unequal masses. And if this kind of a binary system coalesces or merges together, it would produce a burst of gravitational wave, which is a transient high amplitude gravitational wave source. And you could have, given very highly gravitating objects, you could have different combination of these sources: white dwarf, not neutron star, white dwarf, neutron star, black hole, black hole, black hole, and so on. Okay. And because these will all have orbital periods which will vary in terms of their time, the gravitational waves, the continuous gravitational waves, as well as the transient gravitational waves which will be produced here, would sort of lie in different frequency range, and different detectors would sort of cover this frequency range. So that is in general. Now let's come specifically to the sources which are important for pulsar timing array. There are three most likely classes of gravitational wave sources which can be detected by an pulsar-based experiment. The one which the community is going after right now and trying to detect, and probably would be detected or discovered the earliest, is the isotropic stochastic gravitational wave background. But you could, apart from a background, you could also detect gravitational wave from individual supermassive black hole binaries. And in cases where there are coalescence kind of events taking place, you could also detect a gravitational burst source. And in these burst sources, these will be sources with a memory, okay, which would permanently sort of deform the space-time to some extent. So I'll very quickly sort of briefly describe what these three different sources are. So let's start with the isotropic stochastic gravitational wave background. So gravitational wave background is being generated because it is an incoherent superposition of gravitational waves, which is emitted by not one supermassive black hole binary system, but an ensemble of supermassive black hole binary system. So each binary is emitting gravitational wave, and throughout the universe, you have thousands of these binaries. All of them are emitting gravitational waves, and these gravitational waves are superposing over each other and forming a sort of an overall background. And since we are talking of the entire universe and we are sitting inside the universe, to us, this gravitational wave background is isotropic. That is, it is same whichever direction you look at. Okay. So that is what the stochastic gravitational wave background system is there, which essentially is the gravitational wave produced by each and every supermassive black hole binary system present in the universe during its lifetime of about 10 billion years. Okay. And you could do a simple calculation to try and work out what would be the spectrum of this kind of a background. And that was done by Sterl Finney and Jaffe and Becker at the turn of this century. And the spectrum sort of goes as f or nu to the power minus 2 by 3. Okay. So by making some very simplified assumptions, you can actually derive the spectrum. And once you know the spectrum, you could try and build a celestial detector which will detect this background. And that has been the mainstay or the main focus of the pulsar timing arrays for the last 2 decades or so. Of course, you may ask whether such systems do occur, and probably they do. Although there is no conclusive proof that you have a supermassive black hole binary system, there are systems which are very good candidates of that. And one of the such system is called OJ287. This is a final product of merger of 2 galaxies, each galaxy hosting its own supermassive black hole system. Post-merger, these black holes gravitationally capture each other to become a black hole binary system. In the case of OJ287, it has been proposed that you have a 100 billion solar mass black hole, which is going around a 1 billion solar mass black hole. So extreme sort of mass ratios between the two. And observationally, it has been shown that this kind of a black hole binary system is consistent with the electromagnetic signatures, which is essentially flares, which you see here, which are consistent with the model of the system, which has an orbital period of about 12 years and which is having an essentially eccentric orbit. And there are some recent papers, including a Spitzer paper, which has just sort of come out probably a month back or so, which is again sort of confirming that the electromagnetic signatures which you see are consistent with this model of a supermassive black hole binary system. Okay. But the important thing to note is that it has a 12-year orbital period. Okay. So the gravitational wave which would be emitted by the system would have a frequency which will be of the order of tens of years, or would have a period which would be of the order of tens of years. Inverse of that would lead you to a frequency which comes in nanohertz or microhertz. That's the reason I said ultra low frequency gravitational waves are what we are interested in. So this is just one system, but there are other candidates. And if you look through the history of the universe, there will be large number of these sources. And the superposition of all the gravitational waves would become the stochastic gravitational wave background. Now, the spectrum which I earlier sort of showed in the earlier slide, which was nu to the power minus 2 by 3, this spectrum is a very simplified calculation. In actual practice, this spectrum would depend on many things. It would depend on how the universe has been hierarchically assembled from its early stages to the later stages, how the structure formation has taken place. So essentially, there were small galaxies, and these galaxies collided with each other. And as the galaxy merger proceeded, the black hole binary systems sort of evolved. Now, you could have several initial conditions in this evolutionary scenario. You could start with initial black holes which are light, which is called as a light seat model, about 100 solar masses or so. Or you could start with massive black holes, about 10,000 solar mass or so on. You could also have different rates of accretion within the entire thing. So depending on which of these models you believe, the spectrum would actually get modified. It would not just be a simple nu to the power minus 2 by 3. And a lot of work has been done on this. And the plot on the left-hand side shows you the spectrum which you will get for 4 such models. The 4 models are labeled A, B, C, D on the top. And the solid line in each of those plots, which my cursor is pointing out, this solid line is 2 by 3, the canonical spectrum. But you see that depending on which model you choose, the actual spectrum becomes steeper, which means that at a canonical frequency of 10, say 10 to the power 5 into 10 to the power minus 7, the gravitational wave amplitude will actually become smaller than the canonical spectrum. So this has all been worked out by Monte Carlo simulations for these 4 different models: VHM, HOPK, BVRH, and KBD. Okay. And this is a little old paper, so this figure is a little bit old, but the plot on the right-hand side tells you where the PPTA limits are. PPTA limits have evolved a little bit since the time this paper was published, but the shaded region is roughly telling you, given the different models, where you are likely to discover a gravitational wave. Okay. And the dashed curves are the sensitivity of the of the PTAs which you have. So there is a middle dashed curve, which is the Parkes pulsar timing array limits, which were there at 2008. They have sort of improved a little bit since then. And the bottommost triangular dashed line is showing you the limits which one can achieve with the next upcoming largest radio telescope in the world, the Square Kilometre Array. Okay. So certainly with Square Kilometre Array, one should be able to make a very good discovery of gravitational wave from this background. But even in these models, there is a key assumption that the supermassive black hole binary orbits keep shrinking as the time goes by. Now that shrinking is actually driven by friction with the stars, the dynamical friction with the stars and the gas in the centers of the galaxy. But there have been scenarios proposed in which these stars from the center of the galaxy and the gas would actually be ejected out by three-body sort of interactions. And there may come a time when the binary evolution will stall. And this is known as stalled last mile problem. If you apply this stalling algorithm, then these limits become even worse. So from about a strain value of 10 to the power minus 15, you go down to 10 to the power minus 16 or minus 17 for a stalled evolution of the binary. And then you have to figure out how many of these supermassive black hole binary systems are getting stalled. So what I'm trying to sort of say is that there is a lot of flexibility in the models, but what is not there is a lot of flexibility in the limits. The limits have been, as I'll show later on, continuously improving. And as the limits improve, they sort of rule out many of these evolutionary models. And that is one of the astrophysical sort of implication of the pulsar timing array results, which is already happening. Of course, I talked about gravitational wave background, but you can also get gravitational waves from individual sources, which means individual supermassive black hole binary systems. So a single galaxy with two black holes going around each other. Okay. Of course, the strain amplitude which you can detect is going to be, or the strain amplitude which such systems will produce singly or individually would be very, very faint, very, very small. So these will be much harder to detect as compared to stochastic gravitational wave background. But as one would expect, the amplitude would depend on the chirp mass, which is the mass of that, the combined chirp mass of the binary system. And simulations have shown that if one could have a precision of 1 nanosecond measurements in the pulsar timing array, and I would like you to remember this number, 1 nanosecond in the precision of the pulsar timing array, then there is a possibility of detecting at least one resolved supermassive black hole binary system. I say resolved because obviously this individual sources you have to detect against the background. We have already talked about the background. So there is a background and your individual source has to have an intensity which is much larger than this background. So in the plot on the left-hand side, you see a dashed line. So there are 4 plots there. I am pointing out the top left plot. There's a solid line there, and that is the background. And all the asterisks there are the possible individual sources which you can detect. The y-axis there is the precision which you have. So from 1 nanosecond to 10 nanosecond to 100 nanosecond. And the x-axis is the observational frequency, that is the gravitational wave frequency. So given the gravitational wave frequency, the line is the canonical -2/3 background. And given that background, you see that there are very few sources which you can actually detect. And you need to have the right source, and then you can do a calculation how many such sources actually exist in the universe. And the probability is very small. But in principle, you could detect gravitational wave sources from the individual binary black hole systems also. An even more rare source is gravitational wave burst with a memory. Okay. Memory has been proposed in many contexts earlier, but it has been shown that just like a Bremsstrahlung, if you have a massive body moving around another body, it would emit a burst of gravitational waves. And that would probably be a linear memory. But you could also have a coalescence binary system in which a burst may be emitted, which would actually give you a non-linear memory. And the difference between a linear and non-linear memory is in terms of the signal which you see in different polarizations of the gravitational waves. So what PTA would detect is, it would detect that there is a permanent jump in the TOA residuals in terms of this particular memory. So we'll come back to this at a later point of time, but this is a much more rarer event than the other 2 sources which I talked about. But essentially, to summarize, there are 3 different types of sources which you can observe. The most probable and probably the first one which will be discovered is the stochastic gravitational wave background, which is a incoherent superposition of gravitational waves from an ensemble of supermassive black hole binary systems. The second one is the individual sources, and the third one is the gravitational wave burst with a memory. Okay, so much so about the sources. Now, how do we detect these gravitational waves? And as I said in the first slide, we detect them by using pulsar timing array. So let me take a small diversion here to explain what are pulsars. So radio pulsars were discovered about 50 years back by Jocelyn Bell and Anthony Hewish in 1967, where they detected a radio source which pulsed very periodically. And shown here on the right-hand side are the discovery plots of their sources, CP 1919 and so on, discovery around 6th of August 1967, almost 50 years back. And they soon sort of established, and this is now well known, that these radio pulsars are highly magnetized rotating neutron stars, where you see their radio beams because the beam is anchored on the magnetic pole of a rotating neutron star, and this magnetic axis is offset from its rotational axis. And as the animation shows, once in every rotation period, you see a radio beam flash around you, and that is the radio pulses which you see. These are, since neutron stars, they are compact stars, they are very massive, 1.5 times the mass of the sun, and they are extremely compact, radius of the order of about 10 kilometers, and tremendous moment of inertia, 10 to the power 45 grams centimeter square. This massive compact nature means that their rotation is very precise, because to extract the rotational kinetic energy, you need a process which has to be very energetic. And because they have precise rotation, the pulsars show a remarkable clock-like stability, stability of period which is about 1 part in 100 quintillion. Okay. And since they are such a good clock, they play an important role in the detection of gravitational waves, as I'll explain later on. About 2,800 pulsars have been found. And what is plotted on the left is the so-called PP dot diagram, with the x-axis showing the period of the pulsar from about few milliseconds to tens of seconds. And the y-axis is showing you the rate of change of rotation, or rate of change of period, or P dot. Okay. And one can see that these 2,800 pulsars form 3 distinct clusters. The cluster on the top corresponds to pulsars which have very high magnetic field, 10 to the power 14 Gauss or so. The cluster in the middle, which is the most number of stars, have typically magnetic fields of 10 to the power 12 Gauss. And the cluster in the bottom have periods of the order of millisecond and magnetic field of the order of 10 to the power 9 Gauss or so. We are interested for this particular talk in this cluster, which is in the bottom left of this plot, which are known as millisecond pulsars. Since they have a very small magnetic field, and we are talking about neutron stars with very high moment of inertia, the only way they can lose energy is by radiating electromagnetically. And the radiation in this particular case would lose a very small amount of energy. Hence, the millisecond pulsars are the most stable clocks. Out of all these pulsars, the most stable pulsars, clock-like pulsars, are millisecond pulsars. And nearby millisecond pulsars are the ones which are the target for forming a celestial detector for detecting gravitational waves using pulsar timing array. Now, of course, to form an instrument, you have to first time these clocks. And the technique which is used to time the clocks is known as pulsar timing. Let me very briefly explain how pulsar timing works. Okay. So gravitational wave detection involves precision measurements of rotational parameters, how precisely the pulsar is rotating. And to do that, the pulsar timing technique employs keeping track of the rotation cycle of the pulsar. So as you keep track of the rotation cycles of the pulsar over a longer and longer period of time, you have a more precise and better estimate of its frequency or of its period. Okay? Because as the time t, as shown in this expression, increases, for a given phase error which you have, your delta nu precision keeps on increasing. So, for example, in a year, you get a 1 part in 1000 measurement of the phase error, which already gives you 1 part in 12 precision in measurement of the rotation frequency. So one could actually measure the rotation frequency to picosecond sort of level accuracy. And this is at the heart of the precision measurement which is required for discovering gravitational waves, ultra low frequency gravitational waves. Okay. So in the technique, what is done is that the prediction of the pulse time of arrival, when did the pulse arrive at your observatory, that is predicted, and this prediction is compared with a rotational model of the star. And you refine the model based on how much error you have made in a least square sense. The recipe is that you observe the radio pulses and you find a fiducial point on the pulse and you assign a time of arrival to this fiducial point. Since you are observing it in a non-inertial frame, which is at the observatory on the Earth, which is going around the sun, you refer this time of arrival to inertial frame like the solar system barycenter by doing several transformations which are listed here in these expressions. I'll not go into the details of this. And once you have referred it to the solar system barycenter, you then assume a model of the pulsar rotation, which typically involves a frequency of rotation, slowdown in frequency of rotation, omega dot, and higher derivatives. And using this model of rotation, you then predict the next time of arrival of the pulse. You compare the predicted time of arrival of the pulse with the actual observed time of arrival, and then you will get a number which has an integer part, n, and a fractional part. The n is nothing but the predicted pulse number. The fractional part is your error in terms of your prediction. So this fractional part is known as timing residuals. So earlier I was talking of timing residuals of 1 nanosecond, 10 nanoseconds for detecting individual gravitational wave sources. The timing residual which I meant, I have defined now. The timing residual is the fractional part of this difference between the two things. So this timing residual is then minimized in a least square sense, counting each pulse uniquely. And once you do that, you are able to refine the parameters which are there in this model. Now, the model which we have assumed is very simple, is just nu naught, nu dot, nu double dot, and so on. In practice, the model has many parameters, and I'll not go through each of these parameters, but essentially the position of the pulsar, the parallax, the interstellar medium dispersion, if the pulsar is in binary Keplerian parameters, if it's a relativistic binary, post-Keplerian parameters, and many other effects are all included in the timing model of the pulsar. And all of these parameters can be refined from a simple measurement of the time of arrival of the radio pulse. Okay. If you have been able to get a very good model, your timing residuals, which is the fractional part, as I explained earlier, would look like white noise. On the other hand, if your model lacks a particular parameter or is inaccurate in some parameter, you will see systematics in your residuals. And these systematics tell you what to improve in your model. The gravitational wave which we are trying to detect appears as a systemic effect in these timing residuals. Okay. Of course, the effect is of the order of tens of nanosecond or hundreds of nanoseconds. So you need a very high degree of precision to be able to do this. But the fact that this technique is very precise, I am illustrating by showing you a plot on this system called double pulsar, which is the only system which has both the neutron stars seen as radio pulsar systems. In this particular pulsar system, you can time the two pulsars to such a great precision that you can actually predict that the two pulsars are coming closer to each other every day by an accuracy of about 7.152 millimeter with uncertainty in the third decimal place. Okay, and in fact, this system is the best system where general theory of relativity has been tested to a 0.05% significance. So this is just illustrating that you have very high precision measurements possible. In fact, in terms of generally the way the astronomical measurements happen, the pulsar timing measurements have a precision which is unprecedented in astronomy. And as we discussed earlier, we need 1 nanosecond, 10 nanosecond, 100 nanosecond kind of timing residuals for discovering gravitational waves from the sources which I described earlier. So pulsar timing then becomes very handy for detection of gravitational waves. And in fact, the gravitational waves came from pulsar systems. This you must have heard in the earlier talks also. So the first indirect detection of gravitational wave was in a double neutron star system, pulsar B1913 plus 16, which was discovered and timed by Hulse and Taylor and other collaborators. And the plot on the right shows you how closely the prediction of general relativity matches with the shrinkage of the orbit of this particular system. So, having convinced you that, hopefully convinced you that you have here a source which you can use to make high precision measurements, and a source which will play a role in measuring the gravitational wave to the level of hundreds of nanoseconds. Let me now come to the actual pulsar timing array. It's not a new concept. It was proposed back in 70s. And here are the 4 people who have contributed tremendously in sort of developing the concept of pulsar timing array. The principle of the pulsar timing array is that the frequency of the pulsar, so you use pulsar timing technique to measure the frequency of the pulsar clock. This apparent frequency of the pulsar clock will vary due to a perturbation in the metric because of a passing gravitational wave. So as the gravitational wave perturbs the metric through which the electromagnetic signal pulse of the pulsar is passing, the frequency changes, and thus the gravitational wave signature is imprinted on the timing residuals. And if you are sort of looking at a collection of pulsars, not one pulsar, but an ensemble of pulsars, this will be correlated across the ensemble of the pulsar. Okay. So if you can form a celestial detector by observing a sample of pulsars, 20 pulsars, 40 pulsars, 50 pulsars or so, and time their pulses very accurately and try to look for a correlation in their timing residuals, you would be able to discover gravitational waves. So that is, in very simple terms, the principle behind pulsar timing arrays. They are called arrays because you use an array of pulsar. Okay. And this was first proposed by Sazin, who is there on the left-hand side, and later on sort of employed for a few pulsars by Duttweiler. And clear-cut sort of detection strategy was worked out by Baker, who also, by the way, was responsible for the discovery of the first millisecond pulsar. So Baker and Foster in 1990 came up with the details of how a pulsar timing array can be used. And one of the first and most precise experiment, which sort of commenced around 2002, was commenced with Parkes Radio Telescope by Dick Manchester, who is the last person on this particular slide. So it's a very large gravitational wave detector. Unlike LIGO, which is 4 kilometer by 4 kilometer, this has an arm length, which is of the order of parsecs. And the reason why you need such a large detector is very simple, that the frequency is very small. So the wavelength of the gravitational wave which we are talking is extremely large. So the detector, by definition, becomes very, very large. So pulsar timing array provides such a detector with a passive observation of an ensemble of pulsars. So there's nothing active here. We are only doing a passive observations of the pulsars. And such experiments are known as pulsar timing arrays. So a little bit more detail of how this ensemble of pulsar works as a detector. So a passing gravitational wave, so let's say as shown in this plot, there is a wave which is propagating in the z direction with a polarization which is making an angle psi with the x-axis. And you have a tracking signal from a pulsar which is making an angle theta with the direction of propagation of gravitational wave. So this gravitational wave will either retard or advance the travel time of electromagnetic radiation from the pulsar. And this will lead to a timing residual. And that timing residual will translate into an apparent change in frequency delta nu by nu, which is given by this expression here. The terms in blue are called as reception terms because these are terms which are produced near the Earth environment where you are observing the pulsar. And the terms in red are known as emission or pulsar terms because they are happening near the pulsar. Remember that the wavelength of this gravitational wave is very large. So you will have to take into account in certain scenarios both the terms. But if we are talking of stochastic gravitational wave background, then it is isotropic. It is there in every direction. So we can actually sort of forget about the emission term completely, and we can only focus on the reception term. The gravitational wave or signal, because of stochastic gravitational wave background, will be actually correlated across the entire ensemble. And the vagaries of the individual pulsars would not be correlated. So instead of directly detecting the delta nu by nu as in the previous slide, one tries to look for a correlation. And that correlation is basically a function of angle between pulsar 1 and pulsar 2 for a passing gravitational wave. And if you denote that angle by zeta, the correlation function is given by this expression which is shown here. This expression is called as Hellinksen-Down curve. So essentially one is looking for this expression. And if you plot this expression as a function of frequency, this is how it looks. So you have, in some sense, an antenna pattern of your pulsar timing array. And the stochastic gravitational wave background excites the full antenna pattern. And hence, what you detect is the antenna pattern itself, which is the Hellinksen-Down curve. So this is what all the PTAs have been trying to do. Okay. Now, here the assumption is that the gravitational wave has very low frequency, ultra low frequency. So it is a signal which is slowly varying. Okay. But there are other noise sources in this detector which also vary very slowly. Some example of that is uncertainty in solar system ephemeris, or the rotation rate which is of the pulsar itself, which varies slowly, or propagation effects in the interstellar medium which affect the pulse signal, like the dispersion measure, dispersion variation and scattering variation and so on. So there are noise sources in the detector which are covariant or which imitate gravitational wave. And the biggest challenge in discovery of the gravitational wave in the last decade or so has been how to quantify these other red noise sources and eliminate them from the timing residuals in order to detect the very, very faint and small signal of gravitational waves which is present in the timing residuals. There are three major experiments going around in the world. One uses the Parkes radio telescope in New South Wales in Australia, which is called Parkes Pulsar Timing Array. The second one is in North America, which uses the Green Bank radio telescope and the Arecibo telescope. And this experiment is called NanoGrav. And there is one experiment in Europe, which is called as European Pulsar Timing Array, which uses 5 major telescopes in Europe: the Jodrell Bank, the Effelsberg 100-meter telescope, the Nancy radio telescope, Sardinia radio telescope, and the Westerbork synthesis radio telescope. In the last 5 years, in India, we have started our own experiment. So the previous experiment, the PPTA has been in operation for 16 years. NanoGrav has been in operation for about 10 years or 12 years, and EPTA probably 7 or 8 years. In the last 6 years, we have started using the Tata Institute of Fundamental Research's 2 major radio facilities, the upgraded GMRT and the Ooty Radio Telescope, an experiment in India, which is what is called as Indian Pulsar Timing Array Experiment, or INPTA in short. What you see on the top of the slide is the logo for INPTA. This is a collaboration of about 27 people from more than 8 different institutions from India, about 7 faculty members and several postdocs, graduate students, and the undergraduate students are part of this. And I'm speaking on behalf of all of them. So these experiments, what have they achieved till now? what this plot shows you is how the upper limits have evolved as a function of time since 1980s. Okay, so the first millisecond pulsar was discovered in 1980. So from that time to almost today, there is a three magnitude order of improvement as far as the upper limits have come. The gravitational wave background, as I showed earlier in the spectrum, is likely to be between minus say 17 to minus few parts in minus 16. Okay, this is a little older slide. If you put in new calculation, this whole thing has actually gone down a little bit. And we are just on the verge of sort of reaching the sensitivity where the gravitational waves can. So from the various experiments, these are the kind of limits. The limits are shown here in this sixth column for each of the experiment. And you can see that the typical limits are of the order of 1.1 to 3 into 10 to the power minus 15. So the strain values of the order of 1 to 10 to the power minus 15 is already being achieved. And it is possible with the future telescopes like Square Kilometre Array to easily go down to 1 part in 10 to the power minus 16. So in the coming decade or so, we should be able to reach the sensitivity which is required for discovery of the gravitational wave in this particular part of the spectrum. The earlier nu to the power minus 2/3 spectrum, which I showed for the stochastic gravitational wave background, predicted that at 10 to the power minus 15, the gravitational wave should have been detected. And this kind of sensitivity was reached around 2015 or 2016. But no gravitational wave or no Hellingsend down correlation was detected. So the question is why we have not detected stochastic gravitational wave background. In fact, before the LIGO detection in 2017, this was a big question that the sensitivity has been there, what is predicted by the evolutionary models. So why are we not seeing this correlation? Okay. And in fact, that is what prompted further theoretical work, further Monte Carlo simulations, and a deeper look into the hierarchical building models of the universe to try and see if the spectrum is correct or not. And as I showed you earlier, depending on which model you choose, whether you choose a light seed model or a heavy seed model, and whether you choose dynamical friction or not, you could actually arrive at a variety of spectra. And you could also find some kind of a bias in these scaling relations. So people use the Millennium simulation to try and work out what would be the structure formations scenarios. And then they sort of tried to figure out whether the limits of 1 part in 10 to the power minus 15 are realistic, or if you do a more detailed simulation, this detection threshold would get lowered. So I'll not go into the details, but essentially the plots on the left and right are showing you different models A, B, C, where the green model C, this is not in terms of the strain value, it is in terms of the closure density. So it looks slightly different from the earlier spectra. But the green bands are the ones where you don't assume any kind of different types of models, whereas the purple and orange are the models which I discussed earlier. Okay, and one could see from the triangular line, which is the SKA sensitivity, that you need actually a SKA-like telescope to be able to go down to the level where the detection of gravitational wave would actually happen. In 2015, there were several upper limits which were proposed by different PTAs, and those are the asterisks which are shown in both the diagrams. Okay? And those asterisks you see are well above the detection of the gravitational waves. So non-detection of gravitational waves in 2016-18 kind of a scenario only tells us that the evolutionary models which we have assumed for the universe are wrong. Okay. And you need to have more detailed simulations to be able to do that. So in that sense, the PTA limits are already placing constraints on how the merger of galaxies, how the hierarchical structural formation takes place. But it also poses a challenge for us that we still have to continue to work to be able to improve our sensitivity further to detect the gravitational waves. A little word about individual sources, and again, no individual source has been detected so far. However, limits which are worse by an order of magnitude than the stochastic gravitational wave background have been put by different experiments. And the summary is that there's no detection so far, but this also critically and crucially depends on the merger rates of supermassive black hole binary systems. So maybe the rates assumed are not correct, number one. And number two, we need to have higher sensitivity. One thing to remember here is that all these limits have been arrived at by assuming circular systems. If you assume an eccentric system and there is some amount of work which some of the members of INPTA are doing, you might be able to actually sort of lower the limits by at least a factor of 3 or factor of 4 and so on. So there's some work which has been going on in INPTA, some of the members of INPTA as far as the eccentric systems are concerned. But one of the most interesting things which turned out is something very near. So the supermassive black hole binary systems which we are talking about are at redshift of 1 to 2 and 3. So they are very far away systems. But what PTA has actually ended up doing has been to sort of get a more profound understanding of our own solar systems. So it so appears that since in pulsar timing, to be able to measure these frequencies accurately, you have to refer the time of arrival at your observatory, which is known as topocentric time of arrival, to a solar system barycenter. You need to know the position of solar system barycenter to a very high degree of precision. Apparently, the JPL ephemeris, the other solar system ephemeris which we have from space-based observations, are not very accurate enough. In fact, they have uncertainties of hundreds of meters. And the precision with the measurements which the pulsar timing arrays are doing are such that this hundreds of meter precision is not sufficient. So if we apply the PTA results, you can actually determine masses of asteroid belt objects like Ceres, and you can put a limit to that it is about 10 to the power minus 10 solar mass. You can look at the mass of the Jovian system and you can sort of determine it to a large extent. You can even comment on Planet 9, unidentified massive objects in the solar system, which have a dynamical presence as far as the PTA is concerned. And you can improve the planetary mass determinations by a factor of 20. So this is one of the latest results which has come from the PTA, which is more about understanding our own solar system much better. So as I said, that we need to improve, and this is the last part of my talk, we need to improve the precision or sensitivity of the PTA by at least an order of magnitude. And that is where we are hitting with some roadblocks. The first roadblock is already what I have told you, that the solar system barycenter we have to know very precisely. And we are trying to do this using our own data. But in addition to that, we also hit roadblocks because the time of arrival which we associate with the fiducial point of a pulsar is affected by dispersion and multipath scattering in the interstellar medium. And because the interstellar medium is not static, it is turbulent. This time of arrival has a jitter which varies from epoch to epoch of observation. And then this change is very slow. So it is covariant with the gravitational wave signature. So you need to characterize the effect of dispersion and scatter broadening, which is very important for high precision experiments such as PTS. And this is just an example showing you the dispersion measure variation. Dispersion measure is the integrated column density of the electrons, which leads to a delay in the pulse arrival. So one can see that over a period of about 1,000 days, the dispersion measure varies quite a lot for these pulsars. And usually this was corrected by doing 2 frequency observations in PPTA and nanograv. But you need wideband observations to be able to do this. And that is where the Indian pulsar timing array is making a unique contribution. The dispersion effects, basically the propagation effects in the interstellar medium, are a very strong function of frequency. they are much more prominent at low frequency than at high frequency. And the Indian pulsar timing arrays telescopes, they observe, that is UGMRT and UT, they observe at low frequencies from about few hundreds of megahertz to 1 gigahertz. As the plots here show, these are for two pulsars in the PTA, observed using the upgraded GMRT, J1643 minus 1224 and J1939 plus 2134. You see a lot of these effects in our data, basically because we have a 200 megahertz wide bandwidth. The previous experiments I talked about, that is the Parkes pulsar timing array, it only measures about 800 megahertz. It does not go to lower frequencies. Nanograv does measure at 300 megahertz, but their bandwidth is only 20 megahertz. Compared to that, in GMRT, we are measuring from 300 to 500 megahertz. And you can see that in the plot on the right-hand side, which is for a pulsar 1939 plus 2134, the pulse should arrive at the same frequency, at the same time at all frequencies. So the y-axis is the frequency from 300 to 500 megahertz. X-axis is the pulse phase. So ideally speaking, if we knew the dispersion measure of this pulsar accurately, the pulse should have arrived at the same phase right from 300 to 500 megahertz. But you actually see a slope. And actually it's a parabola. That parabola is because dispersion smear is nu to the power minus 2. And in a wideband system like this, it is very easily measurable. The other effect is scatter broadening. So this same pulsar, when you observe at 2 gigahertz or 3 gigahertz, is a very sharp, narrow pulse. But at low frequency, you see that this pulse has got broadened. And that broadening is because of multipath propagation in the interstellar medium. And together, these two effects, and similar kind of broadening you can also see for 1939 plus 2134 in this plot. So because of this broadening and lack of wideband observation at low frequency, the dispersion measures are not very well characterized. And INPTA is actually sort of doing this. So INPTA is actually able to measure this to 4th and 5th decimal places. And the variations, we would be able to compensate for these variations to a large extent in the international pulsar timing array data. And that would be a unique contribution which the INPTA is sort of going to make. In our last 6 months observation, we are already able to go down to 4 decimal places routinely, and in some cases 5th decimal place measurement of dispersion measure. We are also looking at other effects in the pulsar timing, and one of the effects is changing of pulse profiles. So the assumption in pulsar timing is that the profile of the pulsar is the same from one observation to another. It does not change. It's a stable profile. That is not true for some of the pulsars which switch between different profile modes, and these are known as mode changing pulsars. And here is one example, 2124 minus 3358 from our data. So if the shape of the pulsar changes, the time of arrival of the pulsar also changes. And this is a very small effect, maybe of the order of few tenths of microsecond. But when you are talking of tenths of nanosecond or 100 nanosecond precision, it is important. And it is our belief, and there is a group of INPTA astronomers who are working on this problem to show that this pulsar actually shows these kind of profile mode changes. And if we can actually figure these mode changes out, we can compensate for it in the timing data and hence improve the precision of the timing data. So I just sort of illustrated with 2 examples how Indian pulsar timing array experiment can contribute in removing the systematics or improving the precision and sensitivity of the pulsar timing array experiments, and sort of compensating for effects which are slowly varying and act like noise sources towards detection of the almost red signature of the gravitational waves. So I would sort of end here. This is my last slide that which sort of summarizes what I said in the entire talk. So ultra low frequency gravitational waves probe supermassive black hole binary systems, and the clock-like stability of radio pulsars allow discovery of such gravitational waves. However, this requires very high precision and measurements, and such measurements can be done using radio pulsars. So these gravitational waves are then discovered using correlation over an ensemble of pulsars. And there are 3 such experiments operational in worldwide, including a new experiment which has started about 5 to 6 years back in India. And the Indian experiment uses UT and GMRT and is mainly contributing in characterization and removal of red noise due to propagation effects, with measurements up to the 5th decimal place in dispersion measure, as well as some work on progress on emission noise and wideband timing techniques. Okay. In terms of the current state of art, as far as the IPTA's International Pulsar Timing Arrays efforts of detecting gravitational waves is concerned, the best which we have been able to do is to set an upper limit of 1 part in 15, which we are trying to improve by an order of magnitude, which is likely to happen in the next 5 to 10 years. So a discovery is expected in the coming decade. Thank you. Okay, so I'll sort of take questions one by one. So the first question is from Neil Vadodariya. How are pulsar binaries formed, and do we know if it is in a binary system? Pulsar binaries are formed from progenitor stars which are already in binary system. So let's say if you have a sun-like star, say few solar masses bound to another star, and both these stars, they go supernova. That means they finish their nuclear fuel, and at the end of their stellar life cycle, they explode. And by a rare chance, they remain sort of bound. In most of the cases, these explosions are so powerful that they disrupt binaries. However, if it is a white binary or in very specialized tuned conditions, they can still remain bound. Then we are left with a neutron star as a companion to a normal star, or a neutron star as a companion to white dwarf or a neutron star. And that is how the pulsar binary is formed. How do we know if it is in a binary system? Because the frequency of the pulsar will change with the change almost sinusoidally, or will change in a periodic fashion with a period which is same as the orbital period. This is the same way we find how a star is a binary star. We look at their spectrum and we see that their spectral line has a Doppler shift, which is periodic. The periodicity is the orbital period of the binary system. Here we don't look at their spectrum because we have a better way. We know their frequency. The frequency changes as the star approaches us or recedes from us, just like an approaching engine siren changes frequency in a Doppler shift. And if it is happening periodically, that gives us the orbital period and also the other parameters of the star. So that is how we find that it is in a binary system. The next question is, how will the stochastic gravitational wave background affect the frequency of the pulsar? So this I sort of answered a little bit, but I'll go back to that and let me. So if you can see this slide, there is an expression which is given there. So the gravitational wave is sort of encoded in that expression in terms of a dimensionless strain h. So as the gravitational wave passes near the Earth, this will change the frequency of the pulse, electromagnetic pulse, which you are receiving by a very small, tiny amount. And that fractional change delta nu by nu is given by this expression. So that is how one would detect gravitational waves using this kind of a system. The next question is by Sarangi Saraf. How do we identify a memory, and can we differentiate a memory from background? So the strange thing about memory is that it produces a permanent deformation. So identifying the memory would mean that your TOAs or your residuals, which I talked about, these residuals will actually have a constant shift. Now, this effect is very subtle and it has not been detected ever, and is also going to be very rare because you need a massive burst to sort of produce this kind of a detectable effect. But that's the way we can actually identify the memory. And the background will not produce that, but because the background is formed by superposition of continuous gravitational waves. Then there is a question from Rini: Can low frequency gravitational waves interfere? How will that affect our results when we use pulsars for discovering gravitational waves? So, in fact, the low frequency gravitational waves are interfering. I presume you mean interfering, meaning they are adding to with each other, which is what is the stochastic gravitational wave background. That is, it's a incoherent superposition. Okay, so it's not a coherent one; it's an incoherent superposition of the gravitational waves from individual sources, and that forms the overall background. Okay, and I showed you the spectrum, which was nu to the power minus 2 by 3, and I also showed you modifications to that spectrum depending on the evolutionary model. So essentially what we are doing is that our detector is sort of detecting it at different discrete frequencies. So what we are looking for is the amplitude which is expected by this superposition. So in that sense, it is not affecting our results because we are looking for the delta nu by nu which is correlated across pulsars, if I understand your question correctly. So we are already looking at a superposition in some sense. I presume that is what the question was all about. Okay. The fifth question is the memory effect a temporary or a permanent distortion of space-time? Yeah, that's a very good question. Okay. So it is not a temporary distortion, it's a permanent distortion. And that is why LIGO is unlikely to discover a memory. For one simple reason, that the LIGO detector is not a freely falling detector, and secondly, the detector should have a time constant which is much larger than this phenomenon. The LIGO is an instrument in which the time constants are much shorter, so it is unlikely to detect this, and it is also not it's not in a freely falling frame. So any permanent distortion, it would not be able to sort of detect very easily. So LIGO is not sensitive to this. The one of the most sensitive instrument to do this would be in space, which used to be called as LISA, and I presume is still called LISA, which is the laser interferometer in space, which is in between the pulsar timing array detector and the LIGO detector, and that is one of the prime science cases for that is to detect this memory. But certainly, pulsar timing array will also be able to detect this memory. So I guess I have sort of exhausted all the questions in the list. Okay, so we have come to the end of this talk. So before I conclude, let me remind everybody about the next talk in this excellent series. This next talk is on Friday, on May 15th, 2020. And the title of the talk is Gravitational Wave Astronomy uh, with Space-Based Detectors. The talk will be delivered by Professor Rajesh Nayak from IISER Kolkata between 4 to 5 p.m. on Friday, May 15, 2020. Thank you.